All right, so today, as I was saying, we're talking about helicopters. The history of rotary wing aircraft, as the book goes into, I mean, it goes all the way back to kind of the earliest days was Leonardo da Vinci. He drew kind of a design of what they refer to as an air screw that basically was a helical type of wing, I'll call it. And the idea was that if you spun that fast enough, you would screw yourself straight up. Now, some people claim that it could fly, theoretically. There's other people that say, no, it wouldn't work. And they have tried to build it from his drawing. And sorry to say, it never left the ground. But the thought of a helicopter, as we know it now, has been around forever, that you can basically say. Fixed wing aircraft were developed before helicopters, but at the same time, people wanted to do vertical flight, to be able to take off from the ground and go straight up and then move around. The biggest challenge for this was, even after the Wright brothers flew and airplanes started to fly, was to produce vertical lift, you need to produce a huge amount of lift. Thus, we needed, one, a very powerful engine compared to what we had, or even what the Wright brothers had to do their first flight, but also the control of the helicopter is much different, say, from a fixed wing aircraft, okay? Because you got this huge rotor rotating around, okay? Now, what came prior to what we know as a helicopter, what came first is what's known as a gyrocopter, okay? Or a rotor, or a gyroplane, or a gyrocopter. Now, a gyrocopter, okay, I might be having a problem here. I have a feeling the power kind of went out, but I don't know. You know, when a battery backup senses no power?
Wouldn't the camera shut off?
Well, it could be all powered from the power supply.
Hmm. I don't want to push a button because, okay, it stopped by itself. Okay, so what first came was what's known as an autogyro or a gyroplane. All right. There was a gentleman, and sorry, I do not speak Spanish very well, so I call him Juan de la Cerveza, but it's not Cerveza, it's Cerve or something like that. Okay, and I'm sorry that I'm butchering his name. But what he did was he created basically the first practical autogyro. Now, what is an autogyro? In fact, this right here is an autogyro. This autogyro, yes, it does have small wings, which has ailerons. It has vertical fins or stabilizers with a rudder, okay? And it even has an elevator, okay? This actually has an engine with a propeller. So you would think, okay, it is an airplane. And yes, when the engine runs, it creates thrust that pushes the aircraft forward. The conventional controls move the aircraft left and right or roll. That's the ailerons. It yaws with the rudder and it pitches up and down
with the use of the elevator. But the thing that is kind of lacking is they have very, very small wings. And these wings are not truly enough to produce lift. What produces the lift is the rotor blades. Now, what's kind of remarkable is that the rotor blades are not connected to the engine. They're what we refer to as freewheeling. Just like my helicopter here, there's no engine, it just spins by itself, okay? And there is no connection between the rotor and the engine. So the rotor blade is not powered. Well, then how can the rotor blade spin and how can it produce lift? This is what's known as the autorotative force. With the airfoil, when the aircraft starts going forward, because the engine is pushing it forward, air flows over that airfoil. Well, the airfoil then tries to produce lift. But that lift pulls that blade to go forward. So there's an aerodynamic force known as the autorotative force that creates lift and rotates or moves the rotor blade to go forward. The faster we go forward, the faster the rotor blade spins. Now, where this autorotative force occurs is generally like the inner 2/3 of the blade creates that autorotative force. But now, as the rotor blade spins faster and faster, the outer portion, about the 1/3 of the way out, is now traveling fast enough that it does produce lift that will allow the aircraft to go up. Okay? Are we clear on that? It's aerodynamic forces as the aircraft goes forward that makes the rotor blade spin. When they spin fast enough, a portion, and that's the outer portion of the rotor blades, are now turning fast enough that they create enough lift to have the aircraft go up. Somebody say something.
Good. Works.
Does that kind of make sense?
Yep.
Okay. I know it's kind of hard to picture in your mind, like what the hell, air's coming through and making it spin so that, okay. Has anybody ever seen the seeds of a maple tree? Anybody ever live up north?
Yeah.
Okay. And do you know what I'm talking about with the maple seeds?
Mm-hmm. Yep.
If you're unfamiliar, the seed of a maple tree goes like that. There's the seed, and it has kind of this feather attached to it. Okay. And when they fall, they spin around, and that's the autorotative force. Now, the maple tree is kind of smart because it's a way that they can spread their seeds further and further away from the mother tree, if you will. So as they spin, instead of just dropping like a rock, as they spin, they create some lift. And so they can then be carried with the wind further away to propagate the species, okay? Has anybody ever seen one of these people that do what's known as paragliding, where they strap a big fan on their back and they have a parachute? And, sometimes in Davie, there's a park that was a old dump, so it has kind of a large hill, and people will, strap that on, have the parachute, and as they jump off, the engine pushes them forward, but they have a parachute. So as they drag the parachute, the faster they go, the higher they go, because the parachute then produces lift. If they slow down, they go down because they produce less lift. Well, that's the way you can think of an auto gyro, that the rotor blade is kind of like the parachute. As we go forward, aerodynamic forces make the rotor blade spins, and as that spins, it creates lift, and then we can go up and down. So this is kind of what Juan de la Cerveza, kind of created. Now, the biggest problem was controllability, and thus it was easier for him to then use the conventional aircraft ailerons, rudder, elevator, rudder, and ailerons to be able to control pitch the aircraft and that. Now, the one thing is that for an autogyro, you always have to be going forward, because that going forward is what creates the aerodynamic force to keep the rotor blade spinning. Now, to go up, you just can't go up. You have to go faster forward, which then produces more lift to go up. To descend, you slow down the engine, which produces less forward thrust. Thus, the rotor blades don't produce as much lift, and the aircraft goes down. Are we good there?
You're like,
Yes.
Yes, sir.
Okay. Now,
I know
most
that
of the
was-
autogyros today
Huh?
have gotten rid of the ailerons, the rudder, and the vertical
Yeah,
fin.
I don't even know. Who the fuck does that?
I try to tell you, like,
Is that Jordan?
you got
Lucas. Lucas, you're not muted.
Okay. All right, thank you. All right, so early days, they used conventional controls to control the movement of the autogyro. Eventually, what they came up with, and again, Juan de la Cerveza kind of did this, was that instead of having the elevator, rudder, and ailerons, what they did was they made the rotor blade to be able to be controlled. Now, how they controlled it basically was by tilting the rotor blade. So if we can kind of imagine that, you know, the lift is going straight up from the rotor, right? So with a stick, they could actually push forward, and the rotor blade then tilts forward. So as you're flying and that tilts forward, we are now going forward. If we move it to the right, it tilts the whole rotor blade to the right, to the left, and so on. But also what they did, some have a direct, what's known as direct tilt, and that's what I just described. But then what he also did was make each rotor blade to be pitchable. And so when they move the controls, the rotor blade would, a single rotor blade would pitch to move, to increase or decrease its lift so that they could control the helicopter. The autogyro. Now, with that, what we got to keep in mind with autogyros is a couple things. One, that it's the main rotor that creates the lift. The main rotor is not powered by an engine. What turns the rotor blade is the autorotative force, which means that the aerodynamic forces acting on the rotor blade make them spin. Okay. An autogyro cannot take off directly vertical, nor can it hover. It always has to be going forward to stay flying, okay? If you try to stop, you're just going to come down, okay? But you can, as long as you're going forward, you can go. Now, autogyros are inherently, they say, safe, because it's kind of like flying around with a parachute, in that if something happens and the engine quits, well, you come down, but you come down like a maple seed. And as you come down, the rotor blades are spinning, so it's supposed to slow you down before you hit the ground. Okay? But although the autogyro worked, what the lack of being able to take off vertically and land vertically or hover was a great concern. And this is where people still wanted it to be able to do these things. The gentleman that basically developed the modern helicopter is Igor Sikorsky. And what he did, the big problem was trying to have a powered rotor. Because when you power the rotor, remember, for every action, there's an equal reaction. So trying to turn the rotor blade makes the fuselage go in the opposite direction. So they had to come up with a way to overcome that torque. To do that, some people and some helicopters actually have two sets of rotor blades. A very, one on top of the other where they counter rotate. So one rotor blade, as you look down, turns counterclockwise, the top one turns clockwise. So that was one way to do it, okay? Another way people tried was trying to put jets of air coming out the tips, because they're like, oh, if we do that, and most of these things kind of failed. What Igor Sikorsky did was he's the one that developed what's known as the tail rotor. By doing the tail rotor, it's also known as the anti-torque rotor. When the rotor blades spin and the nose wants to go to the right, the tail rotor applies a force to keep the nose straight. Okay, are we good there?
Yep.
I will assume you said yes.
Yes, we did.
Okay. All right, so going on to helicopters. All right, so here is a modern day helicopter. We have the main rotor, we have a small tail rotor, and they are powered by a single engine. Okay, this is what I was talking about, like of a dual rotor system. Now, instead of having one on top of the other, this is a lot of times affectionately called an egg beater, because the rotor blades intermix. There's another famous dual rotor helicopter you may have seen or heard, and that is the Chinook, sometimes referred to as the flying banana, where the rotor blades are in tandem, one in front of the other. Okay, are we good there?
Yep.
Okay. All right, so now we're going into the types of rotor systems, okay? And what I don't, and we're talking about the main rotor system and the types of rotor systems. I don't like how, I'm going to go opposite of how the book goes, all right? I'm going to start with what's known as a fixed rotor system, okay? I'm trying to get into a position that you can almost see me, but every time I try to look forward, the beam just blinds me. Okay. Anyways, we have, let's see. Okay. All right. This is what's known as a fixed rotor blade system. Okay. Or a rigid, sorry, fixed rigid. A rigid rotor blade. A rigid rotor blade, think of my arm as the rotor blade being attached to the center mass or shaft, okay? A rigid rotor blade is one that's rigidly attached, okay? But they do have one pivot point, and that is that the rotor blade can pitch up and pitch down, pitch up and down, okay? Now, that's known as a rigid rotor, okay? Now, I have to kind of go through some things without fully explaining it, all right? But as we go along, we're going to come back to these, all right? And so I'm going to say some things, but I'm not going to fully explain it at this time. Okay, so rigid rotor, the blades can pitch, very similar to what Juan de la Cerveza had developed. And this allowed the aircraft to be able to go forward and to go back, to go to the right, to go to the left. So it was pretty good control, okay? And the helicopter basically had the modern day controls in that they have a center stick, which is known as the cyclic, and they have another control that's called the collective. The collective changes the blade angles of both blades at the same time. Does that make, are we good there?
Yep.
Okay. I don't know. You know what? Let me do this. I'm sorry, I gotta do something on my screen. Okay, I think that will be better for me. Okay, so the collective, if the pilot pulled up on the collective, all the blade angles would increase, thus increasing lift, and the aircraft would go up. To go forward, to the right, to the left, they use what's called the cyclic. The cyclic changes the pitch of the blades independently. So, for example, if we wanted to go forward, the right rotor blade pitches down, the left, in this hand, because it's going back, pitches up. So what happens is the right blade bends down, the right blade goes up, and thus the helicopter pitches nose down, the thrust goes forward, and we now go forward. But we could also go to the right or to the left with the cyclic control. But here was the problem with a fixed rotor blade or a rigid rotor blade system. The blade, because it's so long and trying to produce lift, the rotor blade wants to do what we refer to as flap up, okay? And then other times, the blade wants to flap down. So the blade has this tendency to flap up and down all the time. Well, think about that. If you have pretty much any type of material and you bend it consistently up and down, what's eventually going to happen? It's going to crack and break. So that was not good, okay? That our rotor blades break off. So that rigid rotor system kind of disappeared for quite a long time. Now, rigid rotors have made a comeback. And the main reason, and it's kind of hard to see it on this, but where the rotor blades attach now is what's known as an elastomeric bearing, okay? It's a fancy way to say they connect it with a big block of rubber. And the rubber then allows and takes up the load so that the rotor blade does not break, okay? But in the evolution of the helicopter, we tried the rigid rotor, it had its flaws. So they came up with what is known as a semi-rigid rotor. The semi-rigid rotor blade still allows the blades to pitch, but it also has a hinge that allows the blade to flap up and down. Now the semi-rigid and this is an important part, the semi-rigid is usually what you will find when the helicopter has only two rotor blades, okay? So you have a rotor blade here, you have a rotor blade here, okay? And they are attached to, there's kind of like one big long piece. They have what's known as a teetering hinge, okay? And the important thing to know is that the teetering hinge is above the center line or the span of the rotor blades. This is referred to, hopefully you can read it, is referred to as under slung. Okay? That in a semi-rigid rotor blade, the rotor blade is under slung. Now, what happens with a semi-rigid is this. When one rotor blade wants to go up, the other one flaps down. It's like a teetering hinge. Well, it is a teetering hinge. But keep that in mind. When one goes up, one has to come down. And it is known as underslung. Okay? And this is where, like I said, we're going to get back to these things and why does it need to do these things? So a semi-rigid rotor blade, it has a pitch, the ability to pitch and also teeter or flap up and down. But when one flaps up, one flaps down. The evolution then was to what's known as a fully articulating rotor blade. One of the reasons the fully articulating was developed was that a teetering hinge basically is good for two blades, okay? When they started putting three blades on, they had a problem. There was no real good way to allow the blades to teeter. So what they did, because what we have, it's one of those things that I'll explain later, but what we have to know for right now is that there's another force that tries to make the blades go forward and to go aft, okay? So, as I said, it's kind of, when we get more into it, we're going to see that the blade not only wants to flap up and down, but the blade also wants to do what we refer to as lead and lag, okay? This semi-rigid rotor blade was able to handle that by being what's called underslung. But when we couldn't use the teetering hinge or the semi-rigid, the fully articulating rotor blade allows the blade to pitch up and down. It has a hinge to allow the blade to flap up and down, and has another hinge that allows the blade to lead and lag, okay? So I'm going to go through them once again. There are three types of rotor blade systems. First one is a rigid rotor. Rigid rotor basically just has a hinge that allows the blade to pitch. A semi-rigid rotor blade has a hinge to allow it to pitch, but also to teeter or to flap up and down. Now, in a semi-rigid, when one blade goes up, the other blade goes down. A fully articulating rotor blade independently has a hinge for all the blades, which allows each blade independently to either pitch, to flap up and down, and to lead and lag. And like I said, it's kind of difficult to kind of go, oh yeah, it's just, those are the facts right now. When we go into the next sections and stuff, we'll hopefully understand why these blades are designed this way. Are we good so far?
Yes, sir. Yes.
All right. So next, on page 163. I'm trying to get my eyes adjusted, staring into that beam. Okay, it says forces acting on the main gear, or main rotor, sorry, gravity. All right, so here's our rotor blade, right? Or here's our rotor. They're very long, they're only supported in the center, so gravity has a tendency to make them droop. Yay. Cautionary note, never approach a helicopter when the rotor blades are spinning, unless you're told to do so or you've been trained on how to do it. It has been known to happen that people unaware of what's going to happen with a helicopter as it's powering down, they don't realize that these blades can hang very, very low. And people have come walking up to the helicopter and the rotor blade has removed their head from their body. Okay. And yes, that did cause death. So you got to be careful with that. Okay. The other force acting on a helicopter is the centrifugal force acting on the rotor blade. That's basically the rotor blades are trying to fly away from the helicopter, right? So the rotor blades have to be able to handle the centrifugal force and the gravity, the bending force. And those are pretty straightforward and easy to understand. Lift, okay? So we got gravity trying to pull the blades down, but when they're spinning, it tries to produce lift, so the blades want to bend upwards. Now, one of the things that we said is that when we first started to talk about assembly and rigging and aerodynamics, we said that we have two types of airfoils, asymmetrical and symmetrical. And at that point, I had said that for symmetrical airfoils, it's the same shape above and below the core, where an asymmetrical airfoil has a different shape from top to bottom. And that most aircraft do use an asymmetrical airfoil. And symmetrical airfoils are kind of limited in use. And I said that supersonic aircraft use asymmetrical airfoil. Acrobatic aircraft use asymmetrical airfoil. And also helicopter rotor blades use a symmetrical airfoil. Now, why is this? Well, if you remember when I talked about asymmetrical airfoils, said that an asymmetrical airfoil, when it produces lift, okay, the lift, as the angle of attack increases, the lift moves forward, okay? So at lower angle attacks, the lift may be like about a third of the way back. If we increase the angle of attack, the lift moves forward. If we move it again, it moves forward even further, okay? Well, can you see that if the lift is moving forward as we increase angle of attack, it actually wants to increase or put a force that tries to increase the angle of attack even further. It's just like when you put your hand out of your car window. If you're kind of low angle of attack, your hand doesn't want to really do too much. As you increase angle of attack, it actually tries to twist your hand to a higher angle of attack. Well, with a symmetrical airfoil, the center of lift is practically stationary in that no matter what angle of attack we use, the lift stays at the same location. Well, what that means is that there's less tendency for that rotor blade to have additional forces trying to twist the blade. And with a helicopter's rotor blade, you got to understand that as it rotates around, the angle of attack is continuously changing a lot faster than a fixed wing aircraft. And so that twisting force would put a lot of strain on the rotor blades and could cause them to fail. So it's a way use of a symmetrical airfoil. Yes, we have to have a positive angle of attack to produce lift, okay? But it does minimize the stresses on the rotor blades. Okay. Just bear with me for a second. I know you can't see the board how, can you see the board okay this way?
Yes,
Or not so good?
it's okay.
Is it okay? Because that would make my life easier if I can leave that on. Okay, but I'm going to. That's weird. Oh, okay. Hold on, I gotta do it this way. Okay, there you go. Okay, now I'm gonna do something else. You'll see what I'm trying to do. Okay. It is now the time for the wheel of death. I'll be right back. The wheel of death. Everybody see it?
Yes.
Okay. This is my wheel
Sounds menacing.
of death. Now, as we know, if you watch, I can balance the wheel of death. Pretty good?
Amazing.
Ain't that amazing? Look at that.
Not at all.
All right. So here's the challenge. And usually this is where I like when people aren't here because I ask them to do it. What I'm going to attempt to do, and you tell me if I can do it, I'm just going to use one finger on the edge and balance it in this position. Everybody can see it? Okay.
Yep.
Almost, right? Can I do it?
We're spinning fast
Good
enough.
spinning, yeah.
Ooh, okay. So if I spin it, and yes, I'm only using one finger. Uh-oh, uh-oh, uh-oh. Okay. Any idea why I could do that?
Gyroscopic effect.
Very good. Who is that, Dennis?
No, it's wing.
Lucas? Oh, wait.
Wing.
Oh, sorry, I didn't recognize your voice. Very good. Okay. Two things that a helicopter has to deal with is what's known as the gyroscopic forces. And there are two types of gyroscopic forces. One is known as rigidity in space, and the other is precession. Okay? Because could you see this being, think of the blades going out, right? When this is spinning, we now have a gyroscope. When that helicopter is trying to fly, the problem is that we have rigidity in space. What rigidity in space is that when a spinning object is spinning, kind of, that's why it's spinning object, think that the centrifugal force, it's like 1,000 people are around and they all pull on a rope. What's going to happen? This is going to stay, and I'll do it this way. If I go like this, you can see it's like a top and it's going to stay upright. And that's because the centrifugal force is pulling all equally all around it, so it holds it up straight. Or if I spin it this way, it's going to try to stay in the plane of rotation. The problem is when there's a force that tries to move it out of that plane of rotation, this is where you run into severe problems, okay? So if this is spinning, I can go up and down without a problem because the plane of rotation hasn't moved. If I try to move it like so, it resists and we lose control. Are we good there? And I wish you were here because to just feel what force that is just on a very small diameter wheel, that it's quite remarkable how hard that actually turns. Let me see if I can do this. I don't know. Okay, so if I spin the wheel, when I try, no, I got to, you can't really tell that, but it actually makes me kind of rotate in the seat, but it didn't do a very good job. All right, so that is rigidity in space. Now, you might have noticed that once I got it going and I put my finger on it, notice how I have to rotate it. And the wheel wants to rotate itself. That is the second gyroscopic force. That is because of what's called precession. Precession says that a force acting on a spinning object does not act or acts upon that spinning object 90 degrees in the direction of rotation. So if I spin the wheel as you're viewing it clockwise, if I try to put a force that would try to tilt the top towards me, it won't tilt towards me. What will happen is the force being applied here acts 90 degrees in the direction of rotation. So the wheel kind of feels that it's happening here. And so the wheel's going to turn towards me, not lean towards me, okay? So if I go like so, and I try to pull it towards me, see how the wheel wants to kind of go towards me? And that's not me doing it. So once again, if I turn, I'm going to turn it this way, which is counterclockwise. And when I put my finger here, it naturally should want to fall over this way, but instead the wheel's going to turn towards you. And see how it turned towards you. When I put the force on the other way, it wants to turn the opposite way. And that's known as precession. Okay, so we need to know there are two forces or two gyroscopic forces, rigidity in space and precession. Rigidity in space is that when a spinning object wants to stay in the plane of rotation and resist getting outside of that plane of rotation. We can go up and down, we can kind of go this way because we didn't change the plane. When I try to move it this way, that's when it gets crazy. The second gyroscopic force is precession. Precession says that when a force acts upon a spinning object, it acts 90 degrees in the direction of rotation. By the way, these specifically, the rigidity in space is actually why you can ride a two-wheel bike. In that, now I know some people are able to do this, but if you get it on a two-wheel bike and you don't go forward, what happens? You're going to fall over. You can't really keep your balance, okay? But once you get going and that wheel is going forward, now it's actually the thing that's helping you, if not really allowing you to stay upright without falling over. I'll ask you this question. Has anybody tried to teach a young kid on how to ride a two-wheel bike without training wheels?
Yes.
Amit, I know your kids are young, but one day you're going to have to. Are you there, Amit? Okay. Anyways, trying to teach a young kid, like I taught 3 kids how to ride a two-wheel bike. Well, on the first one, I got really tired trying to, you run behind the person and you're like pushing on the seat. But the thing is that most of the kids, they don't go fast enough. They're going really slow. So the rigidity in space ain't there. So what do? They fall over. So I got tired trying to go faster, go faster. So what I did was I put the bicycle into the car. I took my kid to that mountain or the hill up in Davie. I carried the bike up the hill. I put the kid on the bike and I pushed him down the hill. Because what happened? They had to go fast because they were going downhill. And when they went fast, the wheels spun and they kept them up and they're like, oh, great, this is wonderful. Until
How
what?
big is this hill?
Have you ever seen like a dump? It's a pretty good size hill.
Yeah, it's pretty good size.
Yeah, I mean, it's like the highest point in one of South Florida's.
Yeah, definitely in that area it is.
Yeah. But it's all, it's all landscaped and stuff. But yeah, push them down the hill. They ride really fast until they get to the bottom. Because what happens at the bottom?
They stop.
Yeah, and how they crash. But they get all excited, like, wow, I get it. It's like, yes, see, because you're going faster. To learn how to ride a bike, you gotta go fast. Faster you go, the more stable you are. All right, folks, it is break time, okay? When we get back, we go into more exciting helicopter information. Good?
Sweet.
All right. Okay. So we got done with the gyroscopic forces, rigidity in space, and precession. All right. Next, we go into what's known as the Coriolis effect. All right. I'm not going to put the. Oh, I can. In case I needed it. All right. Make sure this is working. Okay. What is the Coriolis effect? The Coriolis effect, a great way to explain it, hopefully, is if anybody's ever seen, for example, figure skaters. Figure skaters will sit there and like at the end of the routine or during part of the routine, they will start to spin around. And if you notice, when they first get going, their hands are way out. And then as they pull in their hands, they seem to go faster and faster and faster. And then all of a sudden they spread out their arms and they come to a stop. Well, here's the thing. Their speed did not increase. Their rotational RPMs increased, but not their speed. And that is because the conservation of energy. And that if an object, and I'll try and do it on the board, okay? For example, if here is the mass. If this mass going around, let's say, is going 100 miles per hour. Now, I'm going to exaggerate and say the circumference is 100 miles. Okay, so what happens? It takes 1 hour or 1 revolution in 1 hour. Good? Now, if, for example, that mass is now closer to the center, where that is 50 miles, half the distance. Well, it still wants to go 100 miles an hour. So instead of doing 1 RPM, 1 revolution, well, okay, I'm going to go back to 100 miles per hour. It doesn't matter, but it would do 1 revolution in 1 hour. But if we bring in the mass to here, and it's 50 units, okay, it's going to do 2 revolutions per given period of time. All right. So as we get closer, or how we say it is that as the mass gets closer to the center of rotation, the RPMs will want to increase. The velocity is not increasing, but the revolutions per minute are increasing. Okay. Well, here's the thing about a helicopter rotor blade. And this is what they're trying to show in this picture, is that with the helicopter rotor blade, when the rotor blade is kind of flat out, here is the center of mass. But figure now what's happening. As the rotor blade creates lift, it wants to go up. As it goes up, the center of mass gets closer to the center of rotation. So when the blade flaps up,
it also wants to increase its rotational speed, so the blade that flaps up leads. On the other hand, when a blade flaps down, it's going to want to decrease its RPMs, and so that blade wants to lag. Okay, so there's aerodynamic forces and all these, gyroscopic precession, we have rigidity in space, and now we have the Coriolis effect, that as the blade is going through the air, not only does it want to flap up, it wants to lead. Sometimes when it flaps down, it wants to lag. Well, that puts a huge amount of stress on the helicopter rotor blades. Now, as I said earlier, and we're kind of going back to it, a semi-rigid rotor blade, when one blade wants to flap up, the other one has to flap down. So the blade that flaps up wants to lead. The blade that flaps down wants to lag, okay? Well, remember, the semi-rigid rotor blade has a blade, a hinge that allows it to pitch, but not a lead and lag. So how they minimize those forces is by the rotor blade being, remember I said, we got to remember the word, underslung, okay? By having the hinge, the teetering hinge above, right? I'll turn off that front light so that you can kind of see better. Don't know if that helped. See, that doesn't do, let me turn it on. Okay, so with the Coriolis effect, I can't see. You can see that okay, correct? Yeah, okay. All right. By being underslung, when the rotor blade, say this one goes up, okay, the teetering hinge keeps the center of mass roughly the same distance from the center of rotation. Okay, it's kind of like, here's the rotor blade, if on a semi-rigid, because say my head is the teetering point, instead of it just going like this, which this, my hand would get closer to the center of rotation, it goes off to the side. Yeah, it goes, whoa. So this blade has less tendency to want to lead, and this blade flapping down has less tendency to lag. And this is how a semi-rigid rotor blade handles the Coriolis effect. So for example, okay, because remember Friday you could take the final, I'm going to ask some questions. And one of the questions could be, how does a semi-rigid rotor blade handle the Coriolis effect? The answer would be by being underslung, okay? I might ask a question like this. A semi-rigid rotor, a blade that flaps up has a tendency to lead or lag. A blade that flaps up leads. A blade that flaps down lags. All right. Now, a fully articulating rotor blade, how does it handle the Coriolis effect? Well, remember, a fully articulating has a hinge that allows the blade to pitch, to flap, and to lead and lag. So as that rotor blade's spinning around, it can pitch, flap, and lead and lag, all independent of the rest. So there's no need to minimize or have it designed to minimize. It has the hinges to handle those things. Are we good on that? That's the Coriolis effect. I'm waiting, I'm waiting. All right. Going to hovering flight. All right.
We're going to be talking about hovering, flight, torque, and translating tendency or drift. Okay, so hovering flight is pretty straightforward, right? Hey, here we are, we're hovering, you know, and the rotor blades are spinning and we're sitting there hovering above. Well, when they first were doing this, it's like, hey, Joe, get inside the aircraft and let's test hovering. So the test pilot gets in and they're trying to hover. And as they're hovering, what's happening is the aircraft has a tendency to drift to the right. Now and that is known as the translating tendency or drift. Well, what is happening? Keep in mind, when the rotor blades are spinning, the nose of the aircraft wants to go in the opposite direction. So the rotor blade spinning that way, the helicopter is trying to spin in the opposite direction. Now, to correct for this, remember, we had Igor Sikorsky develop the tail rotor. The tail rotor then is putting a force to the right. So now what do we have? We have the torque of the rotor blade trying to make the nose go to the right. We have the tail rotor trying to push the tail to the right to keep the nose straight. Well, two forces trying to push the helicopter to the right makes the aircraft drift to the right. That is the translational tendency or drift. Now, is that a good thing? No, because then the pilot would have to, when they hover, would have to move the cyclic to the left and not directly in the center, which would be the best place for it to be rigged to. So helicopter manufacturers have done one of two things. One, the rigging of the rotor blades are such that the advancing blade has a higher blade angle than the retreating blade. This causes that when we're trying to hover, that it's creating a little lift to the left, okay, to compensate for the torque and the tail rotor forces trying to move it to the right. Other helicopters, the rotor blade isn't directly straight up, but it's actually slightly tilted to the left and thus compensates for that drift. Okay, I would ask you if everybody understood that, but I'm not getting too many responses, so I'm just going to keep on going. Please stop me if you have a question, speak up. Otherwise, I'm just going to keep on going. Density altitude. All right. What we have to understand with density altitude is that as we go up in altitude, the density of the air decreases. Now, what's important about that is when we first talked about lift, yes, we talked about Bernoulli's principle and how an airfoil produces lift. But we also talked about Newton and said that if our aircraft weighs 1,000 pounds, say for the example of the helicopter, for it to be in level flight, meaning hovering, it has to be pushing down 1,000 pounds of air. Now, in this example, we're going to say that 1 unit of air weighs 1 pound, okay? So at sea level, we could say that 1 unit of air weighs 1 pound. So if the helicopter's hovering, it needs to push down 8,000 pounds of air or 1,000 units of air, okay? Now, the problem is, as we go up in altitude, the density of the air decreases. Now, I'm going to exaggerate to make the point, but let's say we get to an altitude at which 1 unit of air no longer weighs 1 pound, but now weighs 0.5 pound. So instead of pushing down 1,000 units of air, if we're at an altitude where the density is half of that, then the helicopter rotor blades now have to push down 2,000 units of air to equal that 1,000 pounds. Okay, and so helicopters are pretty efficient near the ground because it doesn't have to push as much air down. because the airway is more dense. But as we go up, it has to push a greater volume to equal the same amount of weight. Eventually, we get up to an altitude that we cannot push any more air down, and thus that goes to be what's known as the service ceiling of the aircraft. Okay. The one kind of confusing thing with density altitude is a lot of times they use the term high density altitude. And I don't like it because they say high density. But it should kind of be called high altitude density, because what they're asking you is, at a high density altitude, is the density of the air greater or lower? You know, and at high density altitude, the density of the air is low. Low density altitude, the density of the air is high. It's a little confusing there, and I didn't mean to confuse you more, but all right. I'm not hearing anything, so I'm going to go into what's called ground effect. Okay, ground effect. One of the things that determines how much air and volume of air that the rotor blades can push down is, of course, the angle of attack of the blades. Now, remember that the angle of attack is that angle formed between the relative wind and the chord of the airfoil. Now, for fixed wing aircraft, the aircraft is usually moving forward, and thus the air going in the opposite direction of flight with the chord is the angle of attack. But with a helicopter, the rotor blades are spinning, and the air, even if we're going forward, but if we're hovering, the air really is going in the opposite direction of rotation, but also we have a component going straight down. So when we have more what's known as, or how I say, the vertical component of the air is fast, the angle of attack is low. Well, if we're in, or what's known as above ground effect, which is acronym is OGE, okay, we have a lower angle of attack. But when we come closer to the ground, what happens is the vertical velocity of the air decreases because it hits the ground and then has to move away. And because the vertical velocity of the air has decreased, this increases the angle of attack. Thus, at a given power setting and angle of and pitch of the rotor, the aircraft can produce more lift in ground effect, IGE, than OGE. Okay, now it is said that a helicopter is in ground effect when it's within one diameter of the rotor blade. So say a helicopter has a 30-foot diameter rotor blade. As long as it's within 30 feet of the ground, it is said to be in ground effect and can produce more lift than when it's above 30 feet. Well, here's a scenario. Say the helicopter is to lift an additional 1,000 pounds, this log, and we need to go and deliver it somewhere. But the problem is the log weighs 1,000 pounds. In ground effect, the helicopter has no problem lifting the log. But when they get out of ground, or when they go out of ground effect or above 30 feet, they can't push enough air down to lift that additional 1,000 pounds. So how can they go from point A to point B? Well, this is what's known as, it's translational lift. It's another page down, but. So what they do is they lift the weight while they're in ground effect, say within 30 feet.
as they lift up, now they move forward. As they move forward, the vertical velocity of the air has decreased, and thus the angle of attack is now increased. So they come off the ground in ground effect, they start moving forward, and now they can go out of ground effect. But as long as they're going forward, the angle of attack is increased because the vertical velocity has decreased. Now, if when they're out of ground effect, if they try to slow down and hover, they would descend, okay? So what they do is they kind of come in like a fixed wing aircraft. When they get to the airport or where they're going to deliver the payload, they come in, and then once they go below 30 feet, in this case, they're now back again in ground effect, and they can hover, go to the left, go to the right, go backwards, and deliver their payload. And that is known as translational lift. Vertical ascent and descent. Pretty much, this is probably one of the easier ones to know. Hey, if we push more air down than we weigh, we go up. If we push less air than we weigh, we come down. If we push the exact same amount, we stay stationary. We don't go up or we go down. You're making it tough for me today. Just let me know if anybody's there.
I've been talking, my mic's been muted.
No, I know. Okay, thank you.
Go ahead, Bob.
Thank you very much. You know, it's been now another half hour without another person. So, okay. Next, we go into what's called the symmetry of lift. And how I like to say it is, okay, we got Joe, the test pilot, once again. You know, he's the one that figured out that the helicopter drifts to the right when we were trying to hover. So then during the helicopter testing, they're like, okay, Joe, we want you to go forward. Well, they found out another problem, or Joe did. When the helicopter started going forward, the helicopter would roll over and CBD, okay? Now, they didn't expect this to happen, but what is this? This is what's known as the symmetry of lift. When the helicopter is flying forward, let's say, just to give numbers to it, let's say the rotor blades are turning at 100 miles an hour. So when I'm stationary, meaning I'm not moving forward, and the rotor blades are spinning at 100 miles an hour, the advancing blade's going 100, but the retreating blade is also going 100 miles per hour compared to the air, okay? But when we start going forward, and so in that hover, if this is going 100 miles, this is going 100 miles, remember the lift formula. That would be the dynamic pressure. So the lift on the advancing blade and the retreating blade would be the same. But when we move forward, what happens? Let's say we're going 50 miles forward. This blade going forward is not just doing 100 miles through there, but because it's going 50 miles forward, it's going 150 miles an hour. Well, with the same angle of attack, this blade now produces more lift. Whereas the retreating blade, doing 100 miles an hour, but it's going forward, is effectively only going 50 miles an hour through the air. Thus, it loses lift. So what happens? The aircraft rolls over and we die. So we had to figure out a way to overcome this symmetry of lift. Well,
what they did, for example, the semi-rigid rotor blade. When the rotors rotate, okay, the blade that's advancing and producing more lift is allowed to flap up. The retreating blade flaps down. Now this gets, this is where, like I said, there's so many different things that come together. Well, if we remember about the vertical velocity of the air, when the vertical velocity of the air increases, the angle of attack decreases. When the vertical velocity decreases, the angle of attack increases. So when the blade is going forward and we're doing, say, the 100 miles an hour, but we're going 50 miles forward, this blade is allowed to flap up. When it flaps up, the angle of attack decreases, so it produces the same amount of lift as if it was hovering. The retreating blade that lost lift into symmetry of lift now flaps down. When it flaps down, the vertical velocity has decreased, thus increasing the angle of attack of the retreating blade, thus creates more lift, or basically the same lift, because the forward speed or the dynamic pressure has decreased, but the angle of attack has increased. Whereas the advancing blade that flaps up, the vertical velocity decreases, which then, the vertical velocity increases, which then decreases the angle of attack. Although the velocity has increased, the angle of attack has decreased, so they even out. And this way, by allowing the blades to flap up and down, this is how we overcome dissymmetry of lift. Okay, so I'm going to stop right here for a second and kind of try to piece all these together. So for the helicopter, right, as we go forward, they encountered what's called dissymmetry of lift. With dissymmetry of lift, the helicopter wanted to roll over to the left. So to overcome this, they allowed the blades to flap up and down. Now, this corrected the dissymmetry of lift, but it created the Coriolis effect, because when the blade flapped up, it now wanted to lead, and the blade that flapped down wanted to lag. Okay, and so that put undue stress on the helicopter rotor blades. So on a semi-rigid rotor, how they corrected or minimized this Coriolis effect is they made it to be underslung. Now, a fully articulating rotor blade is kind of a smart way to go, because all they did was put all the hinges on it so that it can pitch, flap, lead, and lag. Can you see how they kind of all connect? Dissymmetry of lift, the Coriolis effect, also rigidity in space and the precession, which we didn't totally go into yet, but can you see how they all interconnect?
Yes.
I hope so. All right, so that was the dissymmetry of lift on page 167 and 168. The next that we go into is what's called a retreating blade stall. Well, this kind of lead or follows the dissymmetry of lift, because I'm going to go through dissymmetry of lift once again. As the helicopter goes forward, the advancing rotor blade flaps up. When it flaps up, the angle of attack does what? Say go down. Go down, very good. With the retreating blade, the blade flaps down. When it flaps down, the angle of attack goes up. We've done this, all right, good. Now, at the beginning, when we talked about the fixed wing aircraft, we talked about what's called a stall. And we said that a stall occurs when the airfoil reaches its critical angle of attack, which is a higher angle of attack than normal. Well, and what happened during a fixed wing stall? The nose comes down, okay, because the CG forward of lift. Well, in a helicopter, the advancing blade angle of attack when we're going forward decreases. So the advancing blade won't stall. But the faster we go forward, the retreating blade flaps down faster. Or flaps down more, which increases the angle of attack. Unlike a fixed wing aircraft where most stalls occur at low speeds, because they try to angle up to produce more and more lift, a helicopter normally stalls when it tries to go too fast forward. Because as it travels forward faster, the retreating blade has to flap down faster or more and more, which increases its angle of attack to the critical angle of attack. Now, the crazy thing is that, so we get what's called a retreating blade stall. The retreating blade, right, flaps down and hits its critical angle of attack. And they say it happens between 300 and 270 degrees. Okay, so between here and here is where the airfoil will stall. Now you would think that the helicopter would roll to the left, kind of like the symmetry of lift, but it actually doesn't because of precession. Remember how we said precession is when a force acts upon a spinning object, it doesn't act where it's applied, but 90 degrees in the direction of rotation. So if it happens here, 90 degrees is in the tail of the aircraft. So during a retreating blade stall, the tail actually goes down and not the nose. And it usually occurs at a higher speed. Okay, so a retreating blade stall happens at, or limits how fast the aircraft can go forward because the retreating blade flaps down, which increases its angle of attack. If it reaches its critical angle of attack, this will cause a retreating blade stall. The retreating blade stall happens somewhere between 300 and 270 degrees of rotation. That's over here, okay? Just say to the left of the helicopter. But instead of acting there, due to precession, it acts 90 degrees from the direction of rotation, and thus the nose goes up in a retreating blade stall scenario. On the next, on page 169, that's where we see the retreating blade stall. The next, translational lift, I've already discussed that. That is taking off or lifting up a heavy object in ground effect, then moving forward, flying out of ground effect. And then when we come back in or during out of ground effect, we're not able to just hover, but we come back down into ground effect, which is within one diameter of the rotor blade, to be able to land and maneuver normally. The next is what's known as auto rotation, okay? auto rotation, just like an auto gyro, okay? Is that it's kind of a safety feature on helicopters. In that, in a fixed wing aircraft, if the engine stops, we push the nose down, we let gravity keep us moving forward, which allows us to produce lift. And so that hopefully we can make it to a safe place to land. On a helicopter though, if we lose the engine, the rotor blades really don't want to spin anymore. They're no longer powered. So what the pilot would do is they would push down the collective. This will decrease the pitch of the blades collectively. As the aircraft descends, usually the pilot's going to angle the nose down and it's going to descend. The air flowing over the rotor blades are going to keep them spinning, and they're trying to gain momentum with the rotor blades. The idea is as it's coming down, the rotor blades are spinning very fast, but at a very low angle of attack. As they get close to the ground, they're going to use the momentum of the rotor blades, and they're designed or trained that at a certain height, they then will pull up on the collective. By pulling up on the collective, the angle of attack of all the blades increase, and given that momentum, will produce enough lift to slow down the aircraft in time to land safely. Helicopter pilots train for this a lot. Because the problem is, if you don't train enough, you're probably going to get scared as you're coming down, and you're going to pull up on the collective too soon. So what happens? Oh, you kind of settled it or slowed down, but now the rotor blades stop spinning and you're above the ground, and now you fall like a rock and you crash, burn, and die. Other problem is if you don't pull back soon enough, beating on the collective, you just slam into the ground anyways and you crash, burn, and die. But that is auto rotation. All right, I know it's a little bit early for a break, but I think I need one. So when I get back, we'll do a little bit more talking and we'll see what you guys want to do. All right?
All right.
Anybody have any questions?
No.
Okay,
No, sir.
I'll see you about 9:30.
All right.
Okay. We got up to rotorcraft, controls, page 171. All right. Here's the thing, we don't have that much more, but the things that we went through, yeah, it's a lot. There's a lot of information and such. So really, I'm going to be done for today. We are going to meet back tomorrow. We'll probably do about 2 hours again tomorrow. And that way, they'll give you time to kind of look back over it. What did we go through? I would ask you, please, complete, section C, the online material and stuff like that, so that if you have any questions tomorrow, what we're going to do is we'll be back at 7:30. I'll do a review over what we've covered today. Answer any questions if you have any questions, and then we'll finish off the section, okay? That's the plan. That's what we're going to do. I don't want to just rush through the rest of it and go, okay, so this is what we're ending up doing. If anybody has any questions at this time, please ask.
No, I'm good.
Okay.
Nope.
So, yeah, we're going to meet back again then tomorrow, 7:30. As I said, we will review over what we covered today, and then we'll finish up the section. And, prepare a review for the final that you can take on Friday. All right. Keep in mind, on Monday, is the last, portion of the day is on assembly and rigging. So I will be checking on Monday to make sure everybody gets their online material completed. But then we start landing gear, and I'm just going to say, please read section A, on the landing gear. And do maybe one of the online assignments. And then on Tuesday, we will meet back again, but I will keep you informed of what's happening, but tomorrow I'll definitively say what our schedule is, but I'm looking at Tuesday, doing a Zoom lecture on landing gear. And then most likely Wednesday, Thursday, we will be back into the shop doing landing gear projects. Friday will be online, most likely next Friday. And then we'll, it's a little bit too early let's see how things go for landing gear. But as I said, I want to try and get the projects done by the end of next week. But, by the following week. Yeah, because we got after this week, we have 2.5 weeks left of classes. Are we good?
So next Monday is also a Zoom day, right?
No, not a Zoom day. Monday is for you to finish up anything that you have not completed for rigging.
Mm-hmm.
And also to go over landing gear.
Okay. Okay, gotcha.
I'll say it's like a reading assignment, and if you want to do the questions at that time or watch some of the videos and that, so.
Okay, sure.
And then on Tuesday, we'll resume on, we will resume on Zoom on Tuesday. But tomorrow I'll give you more information and send you out an email also. Okay?
Sounds good, Bob.
All right.
Thank you very
Okay.
much.
Thank you.
I'm gonna
Okay.
kick you all out.
Yeah,
All
have
right.
a nice day.
Y'all have a good one. Enjoy.
Remember,
Yeah, see
tomorrow,
you.